So I guess I was going to talk. Yeah, this is going to be a discussion. So, well, most of the things I've written down today, so perhaps I'll go through them moderately quickly. Um, so, Matt has your tests. He said that you did well. So I don't know what your own standards are. He said the average was something like 80%, which I think is great. So I can't imagine that people are having any problems in this class. So anyway, so we're pretty close to the finish line. So you know what we've done so far. I guess we are right here. And you know what we've been doing. We talked about multi-phase flow of two fluids, capillary pressure, saturation curves, and relative permeability curves to see how multi-phase fluids end up in some location, chimney, a puddle underneath the chimney, and then is held there by capillary forces after it gets there, maybe in a few months, but then is held there for perpetuity. It wouldn't be a problem if they didn't dissolve in small concentrations and were hazardous at even smaller concentrations. And so we talked about the mechanisms by which those would be transmitted downstream by diffusion and advection, just like assignment number 7, with Smithfield site being a type example of that, which I think still exists. It's just an hour north of Niagara Falls in Ontario. I think it is where it is. It's about an hour north of Niagara Falls. And understanding exactly the processes of dispersion, diffusion, and advection. We talked about mechanisms by which it can be delayed and attenuated by sorption, and how we can quantify that, how we can use information on organic carbon and the characteristics of sorption onto organic carbon and fractions of organic carbon to calculate exactly what that behavior is and what the result is. By using the same equations that we use from contaminant hydrology. And we talked about the same fluids in the smear zone, in the vadose zone, and how they can both off-gas by volatilizing, how they're also retarded by a different aqueous and gaseous retardation coefficients, and how washing by rainfall is the most effective way to get them in the groundwater zone. So that's kind of where we are. So I guess the common item in all of these is that we assume that we know some kind of geometry of what they look like, and we don't know yet how to do that. But we will talk about that starting on Thursday, if we get there today. I guess we will. And so we can figure out exactly what the architecture of these things are in situ, the ganglion and the smear zone, the chimney so-called. And we now know enough about the mechanisms by which they get there to know the mechanisms by which they are transported and by which you might want to get them out of the aquifer, because you now know exactly the mechanisms by which you can do it. You know that if you flow a lot of fluid through there as water, you'll pick up some of it, but you won't pick it up in very big concentrations. So you could rationalize that things like pump and treat might last you your whole career and beyond. Don't know if that's a good thing or bad, but you actually have some ideas of the mechanisms that would be applied. And so you'll get to do that in due course. But today we'll talk a bit very simply about mathematical models and how you can use those as adjuncts, if you like, to the analytical model that we just talked about in terms of this graph for concentration versus distance, in being able to figure out exactly what plumes would look like. And we can do those simulations in as we wish to do them. And so that's what we'll talk about it. We'll talk about it in not a simplistic mode, but in a simple introduction. That's my desire today. Didn't want that. Yeah, so this is it. So we'll talk about how we can do this modeling using finite differences. I presume you've seen stuff in your career on campus about solving spatial problems with finite differences. And so we'll kick it off just by talking about an example that I pulled out of a book. And it is about a hazardous waste site, I believe in New Jersey, somewhere on the coastal plain in New Jersey, which was a used landfill. and which was had in a bunch of drinking water wells downstream, detected components which they wanted to get rid of. And so the question is, how do you evaluate exactly how you might remediate such a site to be able to say what the methods are that you'd apply, how long might it take, and in general how you might go about it. So the idea is this. So you pick up some components in this drinking water well. I guess you're staring in a field. You're looking north, south, east, and west. It's got to be coming from somewhere. You don't know necessarily that it's coming from this direction. And so you have to be able to rationalize exactly what you look at. So I suppose one thing to do would be to look at regional wells in the area, to look at the elevations of water levels in those wells, and be able to discern from the gradients exactly which direction the stuff is coming from. Right? So if you end up being able to draw the contours, and so if you take all these existing wells where you have the individual heads at these nodes of this little mesh that you have here, so if you know what those heads are, then maybe you could run a model to be able to predict the distribution of heads. At the same time, you can also go into the wells that you have. You've already done this actually, right? Maybe assignment 2, I can't remember. And take the wells that you have, and if you know the elevations of the water table in those wells, you could put a surface through those to be able to say what the groundwater head contours are. So this is groundwater head contours of H equals whatever. This would be upstream, so this would be progressively higher, and this would be progressively lower. You know that flow is going to be perpendicular to these largely, and so you'd be able to look up from here. Actually, it doesn't work out quite that well here because if you looked perpendicular to the wells here, you'd look in this direction, and it seems that if it's detected here, well, it is kind of that direction, but not quite, right? Slightly off. So maybe it's diffusing sideways and then coming down as a plume as you go downstream. So that's why it's occurring in that behavior. And then the plume is clipping these things, but maybe the maximum concentration would be going down somewhere else, and maybe someone else's problem as well. So if you have the groundwater contours defined, you could take your model and you could look at what the predicted contours were in this model, which is what we'll talk about how you might do today. And you could calibrate this model by changing the permeabilities and the boundary conditions to be able to get a match between what you see, distribution of heads, and what you calculate from the model. And so the easiest way to do that is to take these transects through the site, draw up the head distribution maybe along this transect, along here. And if you do that, you might get a graph like this. And if you have your data, your data, plural, are the red here, you try and relate those to calculations you get by using different magnitudes of hydraulic conductivity in the model. You get a match model to data, then you think that you might have a viable model to be able to work through your system. So then if you take your model, you calibrate it against the drawdown. These are water wells that are pulling out water from the aquifer here and are being impacted by the stuff that's being drawn to them by traveling downstream. And then you look at running the model in forward mode, putting some contaminants somewhere within the mesh corresponding to the location of the buried barrels or mafia dons that are present at the site. And you turn it on to be able to look overprinted on the groundwater flow exactly what the transport of the mass components dissolved in the groundwater system are. And so you run the model to be able to look at the plume and to be able to define how, if you start pumping very heavily out of this area, instead of just pumping for domestic use, you really start pumping water out of this area with interceptor wells, maybe placed here and here, what you can do to mitigate and remove the plume as it goes downstream, so you shrink it over time. So that's the process. So you need a model to be able to represent the groundwater flow. You need to be able to calibrate it against what's going in the system to know what the physical properties are that control the flow. And then once you have that, you run your model to look at what-if scenarios. And the what-if scenarios that you look at would be to look at both the changes in what the groundwater flow patterns would look like, but also how components traveling by advection on the back of that advective velocity would also be affected. So there's two models that we might want to look at, and those are flow models and also transport models. So that's what we'll deal with. So this is it. And so I'm not going to, I could write this out, but I think you might want to get out to cafe sooner rather than later, I'm guessing. Is this your last? You have Thanasis today? Oh. He asked me to escort you over there to make sure you make it. Are only half of you going to Thanasis? Yeah, fine. Yeah. Just the big kids. Yeah, you know by kids I mean young adults, you know. No offense. Yeah, you don't take it. So, we were all big kids and small kids once, and you're young adults, I take it. So, flow and transport. So we know from what we've talked about that we have these relationships which define behavior. For flow, it's the class that you have seen with Byron Parzek or Renee Obringer? No, who did some of you had? Who's the lady who teaches it? Rachel Houseco? Someone had Rachel Houseco? Yeah, 42. So it's either the groundwater flow equation, specific storage, heads, hydraulic conductivities, X and Y directions. It all comes from what we talked about in fluids. This is mass rate of accumulation plus in plus out equals 0. That's exactly what this expression is. And so throwing Darcy's law into this expression somehow gives you this. The transport equation comes exactly the same equation, except now the quantity that you're conserving is not mass of water, which it is in here, but it's dissolved mass in water that is moving downstream. So these are the two expressions that we want. And they come directly from understanding conservation of mass. In this equation, I guess V is volume, this is flow velocity, this is density of water. If you throw Darcy's law in, which is velocity in the x direction is equal to hydraulic conductivity dH dx into here, and you mess around with it, you absolutely get this. And so these are the second order and first order differential equations that we need to deal with, and I guess zeroth order, right? It's changing only in a location, so the order of the dimension is not 1, 2, or 3D, it's 0 at a point, but it's changing with time. So dc dt is a zeroth order equation that changes with time. You know that this is the dispersion part, you know this is advection, you know this is storage of water in the subsurface, you know this is storage of mass of contaminant, and it's affected by this retardation coefficient. And we also know that this is the advective velocity, which is the Darcy velocity divided by porosity. So you know a lot, I think, right? You've discovered a lot through this class. So if we want to be able to represent this class, have you seen finite differences in space before in your classes? Math class, you must have done. Do you still have a math, do you have 220?
Yeah.
What's it, is it matrices? Do you end up solving finite difference equations in there?
We did math 251, which is differential.
Is that analytical solutions or is that numerical solutions like finite differences? Do you solve it using exponential functions and error functions and separation of variables?
I feel like that sounds
My
similar.
God, I feel like that sounds familiar. My head's exploding. Okay, fine. Well, what we'll talk about today is complete in what we'll talk about. The point is that these partial differential equations are pretty straightforward. They represent something very physical. They represent, you can think of it, this gradient dH dx is just the slope of the groundwater table. The contours that we've been looking at previously that define how flow occurs. And of course, the contours of the slope of the groundwater table is the head gradient that through Darcy's law describes the velocity of flow, Darcy velocity of flow. So if you take that this is our differential equation that's defining it, we can think of, if we throw away the accumulation term and look only at steady state, and if we only look at one dimension by looking at the x direction, then we end up with something like this. And so if we want to solve this, we can split this second order PDE into a first order and a differentiation of a first order. So if we can define this behavior, which is very straightforward, we can just define it in terms of taking the dH dx and looking at a finite change in a finite length. Finite change in head in a finite length. So if you look at dividing your aquifer into the x direction and head, and you look at plotting the value of that head at maybe 3 locations as you go downstream, then what you can do is you can calculate what the value of dH dx, which is delta h delta x, which merely says that you linearize these. So you look at a change in head from upstream to downstream, delta h, and you look at how long it takes for that head to change, delta x, and the ratio dH dx is just the ratio of those two lengths. They're both lengths in this particular case. And so if you want to get this derivative, you can calculate it here. And if you call this value, and if we define this behavior in our domain, which is a core, which has 3 nodes in it, downstream node, middle node, and upstream node, and you define those heads as 3, 1, and 0 to represent them, then you can exactly plot those here on this graph. This is how the head changes as you go downstream from this location to this location. We choose to put this directly in the middle so that these delta x's are exactly the same. And if we do that, then the delta h delta x in this part is just the ratio of these two lengths. And we can think of that applying at the midpoint between these 2 points. So we can do that for this point, and the value will be h3 minus h0 divided by the length over which it occurs. Absolutely straightforward. We can also look at these points here in the lower part of the aquifer. We can do the same. We can look at the difference between head 0 and head 1, which is downstream. Delta h is just this height. The length over which it occurs is this. And so this change dH dx over this point in this part here is just this value. And so we have a value for dH dx here, dH dx here, which is great. So that's fine. But we want to know what this second order derivative is. So the second order derivative is the change in head with length over the change in length. So we have values for dH dx both here and here. And those values are these two values here. So if we take each of these two values, subtract the downstream from the upstream, and divide it by the length over which it occurs, we get this. So this is taking dH dx from the downstream portion here, dH dx from the upstream portion, which is here, and saying that they change over this length, which between halfway across here and halfway across here is just delta x. That's it. And so if we want to write out this expression here that we had, then now we know how to do that. We just put these terms together. And so if we realize that delta x is just these two delta x's together, this is delta x squared, we have h1 we have H3, and we have two H0s subtracted. So H1, two H0s, and H3. And so if we rationalize that, we get this. And so if we set it equals 0, we don't care what this is anymore. It could be any value. The only way that this equation can be 0 is if hydraulic conductivity is 0, which it isn't. Otherwise, we wouldn't have a flow problem. Or if the whole sequence of terms in this is equal to 0. So we know that these terms have to be 0. And so the other thing we can do is that if we make these delta x's along the nodes, if you like, within our mesh, the same separations, then we don't care what those are, because we can actually move from, I guess we can only move from this case to this case if we make delta x's the same, both upstream and downstream, right? So we have to do that to be able to simplify it as this. And so this is the basic equation, that if we have a solution where the heads upstream, downstream, and in the middle satisfy this equation, then we've satisfied this equation. Nothing more than that. Super simple. The method's called relaxation, or used to be, I think it's still called that, which means that you just work through the mesh to relax the errors until you have no errors, and you actually satisfy this equation at all nodes in your mesh. And then you have the correct solution, which is the same as the solution we had for New Jersey, which would be some elevation of the water table in one-dimensional flows, or a surface for the water table in two-dimensional flows. So in 1D, we'd end up with this. If we assume that delta x is constant, permeability is constant as well, then we can define this behavior here is the magnitude. And so what we could do is we could, I don't know why I didn't write it this way. I guess this is the kernel term. We could merely write that 0 is equal to 2H0 minus H1 minus H3. And so the alternative, because it comes from this, what we could do is, if we know what the upstream and downstream heads are and divide them by 2, we know what the middle point is. So if you go to this system here, if you knew what H1 was and if you knew what H3 was, if you add those two together and divide by 2, that has to be the value of the intermediate value. Simple as that. So if you had a mesh with a whole bunch of these nodes, you could just sequentially work your way through the mesh, adding the flanking heads together, dividing by 2, and replacing the node that you're standing at with that value, and then moving on to the next location as hopscotch. If you have a two-dimensional problem, like we showed in the example, then you can make a little template that, instead of being this upstream, downstream, and intermediate one, is upstream, downstream, and flanking values. Actually, you don't know whether the flow is in this direction or in this direction. It doesn't matter. But if you look at incorporating now d2h dy squared and do exactly the same thing as we did here in the y direction, you end up being able to show that the head at the middle node on this kind of cruciform template is, you add 1, 2, 3, and 4 together, divide by 4, and that should be the middle value. And if you do it for a three-dimensional problem where you have these x and y, but also now in the z direction, a separation of nodes, where I guess I should mention that your values of delta x's and delta y's don't have to be the same. The mesh can be kind of stretched in one dimension. But if you want to be able to reduce it to get rid of these terms in here, they have to all be the same. And so if you have a mesh that is the same dimensions in each of these three coordinate directions, then this one you take all 6 surrounding nodes, add them together, divided by 6, and that has to be the value of the central one. Incredibly simple. So that's why it's called relaxation. You work through the mesh and you change the value sequentially until you don't, the final time you work through it, you don't have to change them at all. So let's do an example. Super simple. This is our core, this is our upstream, this is our downstream. We had the upstream head here. Instead of just doing 3 nodes, we'll do 4. So we have an intermediate node here, an intermediate node here. We make it 3 meters, 4 nodes, 4 lamp posts, 3 spacings, right? So 3 meters separate 4 different nodes by 1 meter. We have the upstream head is equal to 1 meter. The downstream head is equal to 0 meters. And then, because it's a one-dimensional problem, we use this template. So this template we'd take and we'd first put it over, I think in this case, So if we take this template, and I draw it here, and this template is this node, and this node, and this intermediate node. So that's really what I'm drawing, right? And place it here. Then we can use that. I digress. First of all, let's think about our boundary conditions. So the boundary conditions at this node here are 1 meter, head of 1 meter. Put down this. We're choosing the boundary conditions here as 0 meters for this one. But we don't know what the conditions are here. We still have to solve that. Hence the question. Yeah. Stretching or one question?
Stretching.
So if we put this template on here, then we know that if we add this head to this head, which we don't know, and divide by 2, we get a value. But we don't know what these heads are. So let's guess some. We know that the upstream head is 1, downstream head is 2. We think that for this diffusive process, the values of the heads should somewhere be between those, not less than 0 or more than 1. So we could choose either 0 or 1. Let's just choose 1 for each of those. So if we go in now with the template and we choose a value, I guess I lied. Let's not choose the ones I suggested, but the ones on the other side. So I'm going to choose this and this and this for the first iteration. And so if I take 0 and 1 and add them together, I get 1. If I divide by 2, I get a half, and I put the value here. So now I go back in and I take that template again. Whoops. And instead of using these, the template is now written here. So I take a half and 1 from the previous one, add them together, I get 3 halves, right? I divide by 2 and I get 3/4. I place there. I go back in. Which way do I do this? So now I do this. Do I start and try to think what I did? You could either replace these ones and do it again, or you can do it from, I guess you wouldn't want to do it again. It'd be easier to go back to the other one. So I can take 0 and 3/4 together, add them together and divide by 2. So 0 plus 3/4 is 3/4, divided by 2 is 3/8. And now I take 3/8 and 1 to add together. So 1 is 8/8, so that is 11/8. 11/8 divided by 2 is 11/16. And you just work through like that. And slowly but surely, you get to a stasis where they don't change very much anymore. And so if you keep on doing it, you'd get some small adjustments, but if you keep on doing it, it comes to some static value that doesn't change very much. 171 over 256, I guess it's almost like using binary, right? 2, 4, 8, 16, 32 for storage, the binary base 2 system, and 43 over 128. And so these approximate 2/3 and 1/3. And if you think about it, if you think about Darcy's law, if it's homogeneous, there's no reason why, if the volumetric flow rate is constant along here, and therefore if Q is constant, then area times hydraulic conductivity times dH dx is also constant. If the cross-sectional area is constant and the hydraulic conductivity is constant, by definition the head has to be constant. And if it's constant between a value of 1 upstream and 0 downstream, it has to be a straight line. And if you mark off the heights of that water table against that, you go 1/3 of the way down, you lose 1/3 of the total head, 0.33. If you go 2/3 of the way down, you lose 2/3 of the head, and the remaining head is 0.33. So you can show by reasoning that these are the right results, and they should be the right results. Simple problem. And now, if you know what the values of these head gradients are, you know that delta H over delta X is 1/3 over length of a meter. Therefore, the head gradient is 0.033 over 1, multiplied by whatever the hydraulic conductivity is. Then the Darcy velocity is equal to 1/3. And if you wanted to know what the volumetric flow through this would be, you can calculate it from Q is equal to cross-sectional area times hydraulic conductivity, which I guess we said was 1 meter a second, and dH dx, which is equal to 0.33. And if you have an area, then you have everything to calculate that. And certainly, if you don't have an area, but you just want to know the Darcy's velocity, then multiplying hydraulic conductivity times the gradient of 1/3 gives you the Darcy velocity. If you have the Darcy velocity, by definition, if you know the porosity, you have an advective velocity. If porosity, a not unreasonable value, is 10%, then the advective velocity would be, instead of 0.33 meters a second, it would be 3.3 meters a second. So you have the ability to calculate your advective velocity. So that's what you needed in your analytical solutions to be able to solve for the system for contaminant transport downstream. We had these simple models, you remember, right? That gave us how far it would travel in a given time. If you know the advective velocity and the time taken for it to be released to the time you're looking for it, that length is just the velocity times advective velocity times time. And we know something about the influence of things like Peclet number, which says what the influence of dispersion would be. So if the Peclet number is huge, then we have plug flow. If the Peclet number is smaller, it canters over and becomes more diffuse at the front. And if it's really small, it means that it's not moving at the same advective velocity as we'd expect, because the only mechanism that's driving it downstream is diffusion. So what we could do is we could try and replicate this behavior for this one-dimensional flow by trying to solve the other equation that we have. And the other equation we have is the advection dispersion equation. Again, we can assume actually we can't assume that it's steady state, because that's the essence of the problem. So we want to be able to represent advective transport and dispersive behavior. So I'm not sure it's we'll probably won't talk about how we do this in this class, but certainly advective behavior we can represent, right? So right now what we have is we know what the advective velocity is from this calculation that we did for our core. And we have to represent this first order derivative. Well, turns out that we don't necessarily need to do that. It also turns out that this is quite a difficult equation to solve. Solving second order PDEs is much simpler numerically than solving first order ones because they're unstable when you solve them numerically without doing it the way that we're going to do it today. So what we've done with this second order equation is we've kind of described a mesh that has all these nodes in it from upstream to downstream, and we try and solve how this head is distributed on the framework of this mesh as it goes downstream. The mesh is static. The flow is obviously moving down here, but the mesh is not moving. And so that's fine in taking care of second order derivatives. It turns out not to be very good in terms of first order derivatives. And a much easier way to solve those is by what is referred to as particle tracking. And particle tracking does exactly what it says it does. And that is, you can solve this advective portion of this equation by doing something very simple. You take this rather badly drawn core that we had before, from upstream to downstream. Since we know that the flow is from upstream to downstream for the water, if we entered a mass of some contaminant into it at the upstream portion, we'd have a relative concentration at the upstream boundary condition, and over time it would propagate downstream so that we'd have this curve of this pulse, clean water ahead of it, contaminated water behind it. Maybe it's canted over because of diffusion, but we're not going to worry about that. And so the easiest way to do that is to just release a whole bunch of particles at this point which flowed downstream, carried by the water, and count in all the boxes that we have at these monitoring locations how many of these particles we have. And those you could think of as molecules of this component that is dissolved in water. The more molecules you have, the more particles, or the more particles that have, the more molecules you've had in that given volume of water, and therefore the higher the concentration. That's basically it. And so the idea is we know what the advective velocity is if we know what the Darcy velocity is and the porosity. And we calculated it to be 3.3 meters a second. If we define the velocity as equal to length over time, it's also equal to a length traveled in a given time. We can range that into a length traveled at a velocity over a time step. And so we can calculate how far a particle will have gone by knowing where it is at the beginning of the time step, knowing what the time step length is, and calculating the change in location just by multiplying an advective velocity times the time step. And so if we have an advective velocity of 3.3 meters a second, time step of 1 meter, then it's gone 3.3 meters. And so if we know where it was at the beginning of the time step, it would be 3.3 meters downwind at the end of it. That's it. So that's all we need to do. And so what we would do is we would release particles here, allow them to be carried downstream, allow them to sit in buckets downstream where we can count them. The next time step, we'd release more particles, and they'd just physically motor downstream. And that's what we do. Bless you. And that's how most transport models work, and it utilizes the things that we know about already. If you use methods like this, they work for, this is a very hard equation to solve for Peclet numbers which are greater than about 10. We said before that numbers which are bigger than 10 would give us this very sharp front for 10 onwards. And it turns out that this second order term is difficult to solve by conventional methods like this. Like, since we wrote the differential equations out in terms of a first order derivative, this is dh dx, could be dc dx, and a second order derivative, this could be dc dx, d2c dx squared, just by changing these h's for here. So we could solve it by this relaxation method. It turns out that if we try to do that, it falls apart if we do it for Peclet numbers that are bigger than about 10, because this term here falls apart. Just because, I don't know why it does actually, but it does. But if you want to solve it for Peclet numbers bigger than 10, in other words, where you get a large advective flux but not a very diffusive flux, using this particle tracking method where this term is dominant, this first order derivative term is dominant, then you tend to get pretty good results. So you can use it using particle tracking methods for all Peclet numbers. The only other thing you have to worry about, and we talked about it in terms of solving these advection dispersion equations, we talked about two parameters. Peclet number, which we just talked about. We've said it only works well if the numbers are less than 10 if we use so-called Eulerian methods. In other words, a static mesh, and the contaminant washes through that static mesh, so it sees it going past it, as opposed to Lagrangian methods where you attach yourself to a particle and you go downstream and you end up in a location and you count the number of particles at that location. So fundamentally different. One is a static mesh and you watch the fluid or the contaminants travel through that mesh and solve it for the static mesh. Or you attach yourself to a particle and you move down from node to node to node, which is what we're talking about in terms of particle tracking. And so the accuracy of particle tracking methods is affected what we call the Courant number, or the pore volumes, because it represents basically a very physical idea that if you're traveling downstream at a velocity of an advective velocity, and you have a time step in which you record from going from point A to point B, which is of a certain magnitude, then in one time step you'd have gone a length delta x downstream, right? Advective velocity times time gives the distance that you go downstream. So if you choose in your mesh that the distance between your buckets is smaller than delta x, then in one time step you'll have gone from upstream to a number of nodes downstream, and you'll never have been seen at this node, intermediate node, because you've gone directly downstream. So you want to be able to take a time step which is small enough so it guarantees that every particle that is released from upstream will spend some time at the bucket immediately downstream, not skip right over it, in which case you have no knowledge that it passed through here. So that's basically the idea of stability numbers. So static meshes don't work well with Peclet numbers greater than 10. 1 is probably the number that you should be looking at. And Courant numbers greater than 1 mean that you've completely stepped from upstream to downstream to a lower node, completely skipping over one of these buckets, which means that the accuracy of the model will not be great. And that's it. So that's a clutch version to numerical solutions. So who knows? You may develop numerical models in stuff. You go into grad school, or if you work in a company, probably you'd pick something off the shelf. Lots of models that do these things, but all they do is basically this. Nothing different from this. They may have fancy input GUIs and output GUIs, and they may take a long time to run, and they might look at two-dimensional plan views of plumes or three-dimensional volume models. They may work with things like reaction and retardation, so you might have multiple solute components, just like you're doing with your assignment number 7, where you have 3 components that are dissolved in groundwater and would be traveling with different velocities because of retardation downrange and with different relative concentrations downrange from their starting concentrations. But you can do quite complex things. But basically it boils down to these models are very simple. They try and solve differential equations on some kind of grid. The models are either second order partials or first order partials and zeroth order partials agglomerated in some way. They all represent conservation of mass, either of water, as in this equation, or as dissolved mass, as in the advection dispersion equation. And even though perhaps they can get very complex, the basic ideas of these models and how they work are pretty straightforward, I think. Hope you think also.